Imagine I'm studying some system and then I just come along and hit it with a hammer. What I've done is applied some force, but I've applied it in a tiny, tiny interval. It's like being struck by lightning, an enormous amount of energy, but again, a very tiny interval. So, as we study differential equations, as we study the evolution of a system in time, then we want to come up with a way to deal with these forces that are applied over very, very tiny time intervals. The way we're going to model this is by something called a delta function. I want to begin with something called delta sub a comma epsilon, which is a bit of a weird terminology. But what I mean by this is, well, it has a graph of something that looks like this. As in, it's zero everywhere, except in some interval a to a plus epsilon, and then there the function is just a constant function that has height 1 over epsilon. Here I'm imagining epsilon is just some small number. Now, if I do this, I can then integrate the specific function, and because it's just a rectangle, the base is epsilon, the height is 1 over epsilon, they multiply out to give an area of 1. And since intervals are just the area under a curve, the particular integral of this function is just 1. Now, I want you to imagine that I let that epsilon change. So, for example, if I shrink it down a little bit, I get something that is narrower and taller, or I could go even more extreme and put the epsilon even a smaller value, and I get a larger but thinner spike. Note that when epsilon is very small, 1 over epsilon becomes very, very large. So this is indeed modeling the kind of hammer strikes that I'm imagining. So now I want to take this to an idealized place. I want to imagine epsilon going to 0 and taking some sort of limit. And so instead of it being 0 most of the time and then just 1 over epsilon, which is a big number, I'm going to imagine instead that it actually goes to infinity at the value of a and is 0 everywhere else. Because the integral of those delta functions when I was considering the epsilon were all 1, then I'm also going to have this being true as well, that the integral from 0 up to infinity of this delta sub a is equal to 1 as well. Now, what is this object? It's not really a function because, well, the function value at a is not some number, which is necessary to be a function. But we can call it a generalized function, or sometimes this is called a distribution if one wants to think of it from more sort of a probabilistic perspective. And my goal here is not to try to delve too deeply into what this object really is, but I just want to imagine it as something that's 0 everywhere, and then has an infinite spike specifically at the value of a, and then additionally is going to have the property that when you integrate it out, it's going to be equal to 1. In a sense, we are going to define this so-called generalized function so that it has this nice integral property. Now, before I continue further with this delta function, I want to actually remind you of a theorem from first-year calculus. This is the mean value theorem, not for derivatives as it's most often stated in first-year calculus, but the mean value theorem for integrals. The theorem goes as follows: if you integrate some function over some interval, then this is just equal to the height of the function f of c, where c is some value in between a and b, multiplied by this difference in the interval b minus a. The way the theorem comes about is, okay, well, let me just imagine a graph of some generic function between a and b. Then the integral of this curve from a to b represents, well, the area under the curve. So there's a question, which is, how do I compute the area under that curve? And visually, I'm going to imagine that I have a rectangle instead. And the point here is that the area of this rectangle is the same as the area under the original curve. And specifically, well, the base of the area under the curve is b minus a. The height of the rectangle is just going to be the value of f of c, where c is some point in between a and b. And indeed, I just sort of eyeballed it, but it looks to me like the area under the curve is approximately the same thing as the area of the pink. Sometimes the pink rectangle is above the curve, sometimes it's beneath the curve. Those differences are going to, so nevertheless, the area of the rectangle is equal to the area under the curve, aka the definite integral. This seems quite reasonable to believe that it could be true, and indeed it is always true provided your function f is nice. In particular, it needs to be continuous on the interval a up to b. Okay, so that was a fact. Back to delta functions. I now want to study the integral of the delta function multiplied by some other function. I'm going to do this in the same way by dealing with the sort of finite approximations to the delta function, delta A sub epsilon. Recall the graph as we saw earlier. And as a result of that, what it does is everywhere outside of A to A plus epsilon, it just makes it equal to 0. So I just get rid of that, and the improper integral just turns into an integral from A to A plus E. And then for the height of the delta function, it would just define to be 1 over E, so I'm going to put that in. Let me give some space and get rid of the picture. Well, then what is this? By the mean value theorem for integrals that we just saw, this is going to be the width of the interval, A to A plus epsilon is just a width of epsilon, multiplied by the integrand at some point. So this is epsilon times 1 over epsilon times g of c. And then what about that c? Well, the c is some value in between A and A plus epsilon. It's in the defined interval. The epsilons just cancel, and so I'm just left with g of c. So again, c being some value between A and A plus epsilon. Well, that's all fine, but I want to actually now talk about the actual delta sub A function, or generalized function if you prefer. And so I'm going to take the limit as epsilon goes to 0. Now, there is no epsilon in this expression except for in the constraint on c. Recall that c had to be inside of the interval A to A plus epsilon. And if the epsilon is going to 0, that means that that interval is getting smaller and smaller and smaller. It's just saying that the c has to go to A. In other words, if I go all the way to the delta A function, I will say that the integral of delta A multiplied by some other function g of t is just g of A. So the way I think about this is that the delta function is this sort of infinite spike at the value of A. But even though it's an infinite spike, we had the normalization condition that the integral from 0 to infinity of this thing was nevertheless just equal to 1. So now if I take that and multiply it by some other function g of x, what happens here is that at the spike, it multiplies to 1 times, well, g of A, and then everywhere else is going to be 0. And so it just pulls out the value of the function, just pulls out the g of A. The final thing I want to talk about is the relationship between this delta or impulse function that we've been talking about and a function that we've seen previously in our series on the Laplace transform. Namely, we've seen before step functions. So the way the step function was defined was that it was 0 to the left of A, and then it jumped up to be the value of 1 at the value of A, and was 1 from then on. And indeed, we've seen that this step function played an important role in our study of Laplace transforms to solve differential equations. Now, the step function is discontinuous. So the derivative of the step function at the value of A doesn't really make sense. It's not defined. However, if I imagine taking the derivative at the value of A, what's really going on here is because it's going straight up, it goes from 0 all the way up to 1, it's kind of like having an infinite derivative. And I know if this was back in first year calculus where we were actually talking about functions, you'd say that the derivative of the step function at A did not exist. You'd take some limit as h goes to 0 and show it did not exist. Except we're talking about these sort of generalized functions here. And so I'm going to not deduce a fact, I'm going to define a fact. I'm going to define the derivative of the step function to just be equal to the value of the delta function. Away from A, this is perfectly fine. The step function is just flat, its derivative is 0, as is the delta function. That makes sense. But at the problem spot of t equal to A, this is just a definition. It's a reasonable definition because, as I say, the step function goes straight up, and so it's kind of like having an infinite derivative, and the delta function is infinite at the value of A. So there's some sort of consistency, but nevertheless, this is just a definition. All right, so that was the delta function or the impulse function. We've now studied a few of its properties. In the next video, I actually want to use it to solve differential equations. And so in particular, we're going to figure out what is the Laplace transform of this particular delta function, and then we will use that Laplace transform to help solve differential equations that involve a sort of an impact like hitting the system with a hammer.